Corona mask, Corona haircut. Well, it's pretty obvious that we are currently facing various challenges due to the worldwide pandemic. That's also the reason why this year's Hannover Messe takes place in the digital world. So, welcome to our pre-recorded video presentation, The Evolution of IMA. IMA is the business unit Industrial Media Applications of our Fraunhofer Institute for Digital Media Technology, IDMT, located in Ilmenau in the German federal state Thuringia. In the following minutes, my colleagues will take you on a fascinating journey through the history of this business unit and its various projects and products. Our activities and objectives can be summarized by acoustic process monitoring and quality control using AI. So we capture the audible acoustic emissions of various technical processes and we analyze them by means of artificial intelligence and machine learning algorithms in order to automatically detect faulty parts, compressed air leakages, or deficient welding seams, just to name a few application examples. So enjoy this presentation and feel free to get in touch with us anytime in case you would like to learn more about our approaches and products. Mareike, the stage is yours.
Thank you, and also a warm hello from my side. My name is Mareike and I'm happy to show you around our institute today. We start with our beloved ball system demonstrator, which we use to show our acoustic detection of material faults. We use 3 differently coated balls that all run down a metal slide and all emit a different sound. I will be talking to Judith Liebetrau about it in a second. Judith is the head of our business unit Industrial Media Applications, and but now we will see how this works. Hi Judith, thanks for taking the time for the short interview. And I'm pretty sure after this video our audience is wondering why we chose a ball running system for our demonstrator. Can you tell us something about it?
It's quite simple because we wanted to demonstrate somehow the wearing of ball bearings. We had a cooperation with another Fraunhofer Institute which produce special coating for such bearings to make they last longer, and so we decided to have a nice joint demonstrator on this topic.
Can you tell us a bit more about the experimental design?
Yeah, we have 3 different balls. One was coated with a special coat from the colleagues of us. Then we have a normal coated ball and a damaged one, and they are spinning around in this ball track. And only by the noise they make during the side and the rolling, we detect which ball is rolling down. So we detect the 41, the normal one, or the special coated one.
Cool, but pretty sure there were some challenges.
You can imagine that on a fair it's very loud, crowded, people are touching your demonstrator, and if you're recording the sound of balls, that you have to make sure that the background noise will not interfere. It's the same if you're going to the protection, so if you have a bearing implemented somewhere, there will be other machinery part and you have to somehow to calculate them out of your sound. And the boards are rolling by chance through the demonstrator, so you have to make sure to detect the real one you want to know the sound of. So these are the problems we had to tackle.
All right, sounds very interesting. Thank you, Judith, and we will hear you later for the Q&A after this video. And we will now see how we went on with our industrial media applications experiments.
So have fun.
The next experiment that we did cannot be shown here at our institute because we did it in cooperation with the Ilmenau University of Technology. But we prepared a video for you. Im Bereich der luftschallbasierten Leckagendetektion setzt man heute auf das bloße Gehör von geschultem Personal oder auf Prüfverfahren mittels Ultraschall. Die Wissenschaftler des Fraunhofer IDMT haben in einem Experiment untersucht, ob sich das Gehör des geschulten Experten durch den Einsatz neuronaler Netze nachbilden lässt. Das Ziel ist, ein zuverlässiges Messsystem zu entwickeln, mit dem Leckagen anhand der hörbaren Schallemission automatisch erkannt werden. Erste Untersuchungen zeigen, dass eine Leckagendetektion mittels Luftschall im hörbaren Bereich unter Verwendung von maschinellen Lernverfahren generell möglich ist. Getestet wurde unter Laborbedingungen. Die Wissenschaftler haben Geräusche einer einstellbaren Leckage an einer pneumatischen Vorrichtung gemessen, in unterschiedlichen Abständen, mit und ohne Hintergrundschall. Die Daten wurden dann mit Hilfe eines neuronalen Netzes analysiert. Bei der Analyse ohne Störschall konnte sofort eine Erkennungsrate von über 98% erzielt werden. Mit eingespieltem Hintergrundlärm, so wie er in Produktionsumgebungen vorkommt, lag die Erkennungsrate immerhin bei 75%. Maschinenbetreiber und Anlagenführer stehen vor ganz unterschiedlichen Problemstellungen, was die Geräuschkulisse in ihren Produktionsumgebungen betrifft. Am Fraunhofer IDMT wird derzeit untersucht, welche Herausforderungen die Datengewinnung, die Annotation und Datenqualität sowie die sichere Datenverarbeitung mit sich bringen, um so ein zuverlässiges Messverfahren auf Grundlage von Luftschallanalyse und maschineller Lernverfahren zu entwickeln. So now you have an impression of what we did in the field of leakage detection, and I invited my colleague David Johnson, who's mainly responsible for the research in this topic. Hi David, thank you for your time. And can you tell us something about the new Fraunhofer IDMT detection method?
Yeah, sure, Marika, thanks for having me. So as we saw in the video, typically compressed air is usually detected using ultrasonic sensors, which can be kind of susceptible to noise and other issues. So in our detection method, we evaluate and use traditional measurement microphones to record sound in the audible hearing range. So this is kind of taking advantage of what trained professionals might hear when monitoring the systems manually. So we find this actually to be a pretty profitable market, as compressed air is one of the most expensive energy sources. So by helping reduce the amount of leaks in such a system, there can be significant savings for manufacturing companies.
Cool. And how much data did you record for your experiment?
Yeah, the experiments were all done within a laboratory environment, and we performed 3 different recording sessions to ensure that there's variation in the data to help reduce bias during the model training process. So during each recording session, we actually had 4 microphones in different locations so that we could get an idea of where to best place the microphones. And additionally, we simulated different types of background noise every time to ensure more lifelike recording conditions. But in total, we ended up with about 10 hours of data per recording session. And we can use those then to train our machine learning models. So the more details about this data set can be found on the IDMT website. And additionally, we've published a paper within the Internoise 2020 symposium.
Okay, thank you for your time, David. I will now show our next demonstrator, which also has something to do with compressed air, but in a totally different use case. You might already hear it in the background. That's the really loud noise of the fans in the air hockey table that blow up the air so the pucks can slide easily. And if you wonder what we show with this demonstrator, my colleague Sascha Krollmisch will explain it after a short video clip. And unfortunately, we cannot have a match together this year. Sasha, we are all curious about where the idea for this demonstrator came from.
So we wanted to have something where the people can also interact on the trade show. So not only we show them something and they see what happens, but they can directly play, and during playing basically figure out what our technologies are capable of. And we had several options, but we decided for the air-hoc table since it's a fun game, basically everyone knows and everyone has fun with.
And what is actually shown with the demonstrator?
So with this demonstrator, we show that we can, just using microphones, detect the materials of the plastic puck. So basically when someone is playing with a puck, the puck hits the boundaries of the table and the microphones record that signal and can directly say of which material the puck is made of.
Okay, and why did you only use acoustic sensors and not optical, for example?
So, well, in this case, just for the material detection, we could also use cameras since the materials have a different color. This would not work if we would have printed them in the same color. And furthermore, we also, using this technology, can figure out if something is broken inside a puck. So if there's like little air inside that shouldn't be there, you can hear it and we can therefore classify it. And this would be impossible with a camera unless you cut the puck open, which of course destroys it.
What technology is used for this demonstrator and what is the difference to the other demonstrators?
So as in the other demonstrators, we also use audio pre-processing to get the data in the right format. And then we have a neural network which classifies the different sounds. And the main difference to the other demonstrators is that in this time we have a more long-term recording and we have several just very short hit events that we have to distinguish, while the other demonstrators, for example, the metal ball or the engine demonstrator, have more stable sounds that we need to differentiate and classify.
Okay, so we already saw the ball demonstrator, but what is the engine demonstrator about?
It's also a very nice demonstrator. I think my colleague Sai can tell you more about that in the next room.
Okay, I will have a look. Thank you, Sasha.
You're welcome.
Bitte vergessen Sie Ihren Mund-Nasenschutz nicht. Danke, dass Sie an Ihren Mund-Nasenschutz gedacht haben.
Hi, Sai. Why is there a smartphone lying on the demonstrator?
I'm monitoring the conditions of the engine.
What are the main advantages of using a smartphone?
The main advantage is energy efficiency. It only takes less processing power to process our algorithm and providing the results. So it does not require any high-end processors like conventional approach. And in terms of storage, it only requires few megabytes to store our model information. And in terms of latency, so you don't need to use any cloud data stream. Basically, cloud connectivity adds latency to your application. And there are privacy concerns when the information transmitted to cloud.
So that means the data are pretty safe.
Yes, it is.
And how do you transfer the algorithms from your computer to the smartphone?
Actually, there are different approaches involving in the transferring algorithms onto smartphone. TensorFlow and ARM microcontrollers providing energy efficient libraries where you can use their pruning and quantization approach to reduce the size of your model at the same time without compromising the accuracy. And libraries they are providing maximizes the performance at the same time minimizing the memory requirements.
That doesn't sound easy at all.
Yes, there are multiple challenges involving in the deployment process because since you have limited resources on your mobile, you need to limit your parameters of your model and number of operations. So it takes a lot of optimization process.
Who will be using this approach?
We're offering this application to the companies who want to use energy efficient algorithms for acoustic condition monitoring, predictive maintenance, and anomaly detection.
Okay, cool. So let me know whenever there's new results and I will be talking about them to our audience.
Yeah,
Thank you, Sai. The next experiment that we will show is again conducted in cooperation with the Ilmenau University of Technology, specifically with the Fachgebiet Fertigungstechnik. What we did in the ARCOS project is also shown in the next video because we cannot be there right now. And after this video, we will hear my colleague Kadi Breitbart, who is involved in the project and can give some information about the current research state. I'm happy that my colleague Kati Breitbart found some time to give us a short insight into this project. And Kati, what are the current findings? Are there any results that you can give an insight on?
Yes, the last month we did a lot of experiments to find the right position for our sensors. Clearly we know now that we can hear the acoustic differences, but we have to see how stable and robust our algorithms are running. And one further research question is how adaptive are our algorithms? At the moment in ARCOS we focus on constant parameters over the entire running time, and we just vary the process parameters itself to get a good or bad welding seam, while for example material and length of the welding seam remain the same.
Okay, and what are the next steps and when do you plan to finish this project?
Our big challenge at the moment is to get a good data set. Unfortunately, our measurements are interrupted due to the current situation because we cannot be at the test site, especially in the industrial environment. But our first measurements at the laboratory should show if we can hear something and if it's possible to give a statement about the condition of the welding seam up to 100%, because this is really important. Then in the industrial environment, the quality of welding seams often is a safety requirement. And I think the manufacturers in the automotive industry, for example, know what I'm talking about. So we will now go on with measurements, then testing and optimizing our algorithms, and hopefully finish the project successfully next year in the summer.
Okay, thank you for your time, Kati. And let's hope that you can go on with your measurements as planned and finish next summer. And but for this summer, we actually work on something that is the outcome of all of our experiments and projects that we did so far. And it is the prototype of our new software, ISAAC. Right now, only our data scientists use this framework for retraining and training their models based on acoustic data. However, we want to prepare this software to give it out to operators of industrial quality assurance systems. So ISAAC is made for users with little AI knowledge as well as for AI experts. We will make sure that applicants get the instructions they need to successfully train and retrain their own models to apply it to their very own use case. I've talked to my colleague Tanja Krüger, who's mainly involved in the development of our software IDMT-ISAAC. Hi Tanja, thank you for your time. And would you tell us something about ISAAC, for what it stands and how it works?
ISAAC means Industrial Sound Analysis for Automated Quality Control. And the idea behind is to provide a quality assurance employee with a tool with which he can make better and faster decisions for his project or for his work. And pre-trained models based on a customer process are made available in this tool and can be later retrained for new data. And in the future, it could be possible to combine more data through data fusion in order to increase the robustness of the models, for example, by using real-time machine data. And important thing is we don't want to compete with the big players in the market, but use our approach to close a niche for small and medium-sized companies in Germany. The niche includes predictive maintenance and quality assurance with the help of acoustic monitoring based on data-based artificial intelligence tools.
And can you tell our audience how they can integrate it into their existing quality assurance software?
The integration depends on the customer's running system. From the beginning, ISAAC is conceived as a standalone software tool. You can include ISAAC as an add-on into an existing production line to support the employees. Also, data from other systems or machines can be included, example over APIs.
Now the question of all questions, where can I buy it?
At the moment, ISAAC is not a final product. We have a prototype that we want to evaluate and develop with our partners and customers who know their needs and help us to create a valuable product.
Thank you for your time, Tanja. And who wants to get further information on the development of our IDMT-ISAAC software is welcome to join our network on acoustic monitoring of manufacturing processes called IMAMF, which is a project funded by the Federal Ministry of Education and Research, BMWF. For more information, you can go to our website. And I'm happy to receive your registration for the online event on June 10th and 11th. And now my colleague Judith Liebetrau will answer any of your questions on our research. And I hope you enjoyed our little time travel, the evolution of IMA. And with this, we return to the studio in Hannover.